Hello everyone, my name is Zhihan Fang from Rutgers University. Today it's my great honor to present our work named CellSense, Human Mobility Recovery via Cellular Network Data Enhancement. This is a joint work of Rutgers and the Shenzhen Institute of Advanced Technology in China. This is an outline of my presentation. First, I will give you a short introduction. As we know, human mobility modeling is important for many real-world applications, like mobile computing, urban planning, and location-based services. Cellular building records is one of the most important data sources for human mobility modeling due to its high penetration rate and low collection cost. However, there is one major problem in cellular building data, which is data sparsity, because the data is collected with human activities, like calling a phone or connecting through internet. In this paper, we want to provide a method for data recovery on CBR data for a fine-grained human mobility modeling. To achieve this goal, there are two major challenges. First, as the level figure shows, more than half cell phone users visit more than one new location every week, and around 20% of users visit more than 8 new locations. This will introduce challenges for mobility estimation and data recovery because we don't have historical data for the new locations for the specific user. Second, at the right figure shows, there is a high uncertainty in the sensing granularity among users. The sensing interval differs significantly among users. Around 73% of users has a sensing granularity that is larger than 1 minute, while 26% of users, the time interval, the sensing granularity is larger than 10 minutes. Many works has been done on human mobility study on cellular building data. So we can use a two-dimensional table, like here, to categorize all the works. One dimension can be continuity for achieving either continuous or discontinuous mobility. The other dimension is at the level of mobility, at the collective or individual level mobility. After we feed all the works into this table, we find there is an empty space, which is a combination of continuous and individual level mobility. That's where we can uniquely position our work. So to summarize, our target problem is to recover missing observations of individual human mobility in sparse cellular building record data. So that's the short introduction. Then next is a design. This is the data set we use, CBR data collected by a major network operator in the city, and some open source data like open roadmap data. To solve uncertainty and data sparsity on individual user data, we designed a system with two major components. One is the left side collective mobility modeling. The other is on the right side convex well individual mobility modeling. In the first step, we estimate the average travel time on mobility graph based on collective user mobility patterns. In the second step, we estimate the location of and the modality of individual users based on machine learning solution. For the collective mobility inference, first we have this route and status inference. We create a mobility graph, then select the road candidates, then apply the pruning method to reduce number of candidates. We also have this status estimation for individual users with the status of the individual based on his data or historical observations. So the travel time inference is built on the routing status inference. We estimate the travel time by a Gaussian distribution The second step, then apply a expectation maximization method by joining optimize the travel time and the routes of individual users. For the individual mobility inference, we use a bidirectional GRU network to integrate both past and future individual mobility records. Also, the collective mobility we got from the collective mobility inference module, the travel time especially. And also, to integrate the contextual data, like we mentioned in the previous slides, the road network data. So next is our evaluation. The metric we use is geographic distance to estimate the estimation error. We have 3 baselines. One is hidden market model. Second one is deep transport based on a LSTM model. Third one is a trait gem, is a trait generation method based on the statistical features of the user mobility. So that's the evaluation result. We find our model can always show a lower estimation error. So in conclusion, we start with a sparse CPR data and design a data recovery system with 2 components to achieve the dense mobility data. Thank you. That's my presentation.